When I was in 6th grade, I learned about functions for the first time. Like this one, y equals 2x. You put in one thing, and it gives you back 2. Nice. And then I went to high school and took pre-calculus. And that class went something like this. You guys like f of x equals x squared, right? Now, what if I make it f of x equals x squared plus y squared?
Domain expansion. Multivariable.
And now, you can graph cylinders and spheres and surfaces and planes and helices, all using mathematical equations in 3D.
Okay, maybe it wasn't that epic. But that idea, the expansion of old concepts into new domains, is a key cornerstone of mathematics. And it's applicable to so many different areas, including calculus and integration. And today, that's exactly what I'm going to do. Take the idea of an ordinary 1D integral and expand it to higher dimensions to describe line integrals. I had promised in a previous video I would give a more detailed explanation of these, and so here it is. Going into this video, I'm going to assume that you have a basic understanding of how integration is done in 1D calculus. I'm also going to assume you're somewhat familiar with the concept of an input space, vector-valued functions, and parameterization of curves. If you're not, I would suggest watching my previous video on this topic. In this video, I'll be talking solely about the basics of line integrals, where they come from, the intuition behind them, and how to calculate them for ordinary functions. I won't be talking about line integrals over vector fields. That's a topic I'm going to save for a different video since there's significantly more depth and nuance to go into. So, let's get into it. To talk about line integrals, let's first start in single variable or 1D calculus with ordinary 1D integrals. We'll see that line integrals are actually a pretty simple extension of regular integration into higher dimensions. I mean, that's really what multivariable calculus is all about. Recall that 1D calculus is called 1D because we're working with functions with only one input variable, denoted x, meaning that our input space is one-dimensional. We always have one output variable, denoted y. This means we can graph our function's input and output in 2D. Let's use a relatively simple example, the function square root of x. The traditional concept of a 1D integral involves taking the area under this curve, and that's definitely true, but let's look at it through a different lens. Let's bring ourselves down to one dimension, the x dimension. This right here is our input space. The input space is the set of all possible values for our input, which for us is just the real numbers. If this term is unfamiliar to you, check out my previous video on vectors and vector fields, where I define it in a relevant context. So back to our 1D input space. Here, x increases as we move to the right and decreases as we move to the left. At each point on this x line, there's an associated y value, or output value. I'm just labeling the output value corresponding to each input point. Great, now let's start the process of integrating. We write our integral in this form, integral of f of x dx between some bounds of x. Let's pick 1 and 9 for our bounds for the sake of demonstration. This dx tells us to take an infinitesimal step in the x direction, and since we're going from an initial value of 1 to a final value of 9, we'll move in the positive x direction. Note that this is one of the two possible directions in our 1D input space. We can either move to the right along this horizontal line or to the left, and here we choose to move to the right. We multiply the width of this infinitesimal step by the output value assigned to our starting point, which here is the square root of 1, which is just 1. Since our dx is infinitesimally small, the output value at our starting point and our next point, x equals 1 plus dx, are pretty much the same. We keep doing this over the entire length of the x-axis that we specified, from x equals 1 to x equals 9, and add up each little product of dx and f of x. That's our total integral, which is a single scalar value. That's precisely what the symbols mean as well, summing up all the products of f of x and dx from x equals 1 to x equals 9. Okay, that's great, but how about in higher dimensions? Well, I'm glad you asked. Let's move to 3 dimensions using the example function f of xy equals x squared plus y squared.
Domain expansion.
You can see the output of this function extending in and out of the page in the z direction. Now, let's look only at the input space of this function, which is the 2D xy plane, and think about taking an integral. Remember, with a 1D input space, we could only move in 2 directions, increasing x or decreasing x. Now that our input space is 2D, we have a lot more directions we can move in, infinitely many, in fact. And we don't even have to move in a straight line. We can move in squiggly lines or curves too. So, we need to ask a slightly different question. What is the integral of our function, f of x comma y, as we move along this curve? Or this one? Or this one? Now, how do we write such an integral mathematically? For a 2D input space, we would write this as the integral of f of x comma y ds over a curve c. Here, the curve c is a line we're integrating over. F of xy is the output of our 3D function, and ds is an infinitesimally small movement along c. The only difference between this and an ordinary integral in 1D calculus is that in 1D calculus, your curve c was actually just the x-axis, and therefore your ds was just dx. This idea of taking an integral over a line may seem abstract, but remember, we did the exact same thing in 1D calculus. Let me demonstrate intuitively how it's done. Let's say we want to calculate the integral of our function f of x comma y equals x squared plus y squared over a line segment going from 1 comma 1 to 3 comma 3. Here's how that integral is calculated. We'll start at 1 comma 1, find the output of our function at this point, which is just 2. We then multiply that by an infinitesimally small piece of our line segment, which we'll call ds, which moves us to a new point on our line segment. At this new point, we'd find the output of our function, and again, multiply it by ds. We'd continue this for every point on the line segment, adding up all those products of the function outputs and infinitesimal steps along the integrating line to get the final value of the integral. In this case, that just so happens to come out to 52 root 2 over 3. Now, an appropriate follow-up question would be, how do we actually get to that number? And the answer isn't obvious. Our ds is dependent on both the x and y coordinates, so it gets a little bit more complicated to describe what an infinitesimal step ds actually looks like mathematically. But before I go there, I want to address a question that may be lingering in some of your curious minds. With 1D input spaces, in other words, in ordinary 1D calculus, we could only take an integral over a line, which was the x-axis. With 2D input spaces, we can take integrals over any line or curve existing in 2D space. But can we not also take integrals over 2D surfaces now? Lines are 1D shapes, and surfaces are 2D shapes. So now that we have a 2D input space, can we take integrals over 2D surfaces? And the answer is yes, we can. That's how surface integrals work. To get there, we'd have to start talking about multidimensional integrals. In other words, integrals in more than one direction at the same time. This is different from making our functions themselves multidimensional, so I won't be talking about surface integrals in this video. I just wanted to point this nuance out to demonstrate what a line integral really is. Line integrals are 1D integrals. They're integrals you take moving in one direction along a 1D shape, which is line, and they end up producing areas. This contrasts with surface integrals, which are 2D integrals. Integrals you take moving along two different directions over a 2D shape, which is a surface. 2D integrals generate volumes. There's a figure online that I really like, which shows what line integrals really look like. Here it is. They can still be thought of as areas. Just now, these areas are along a squiggly path that can exist in 3 dimensions. Okay, now that we've cleared up that nuance, let's go back and actually try to calculate these line integrals. Or at very least, turn this abstract mathematical expression into an expression that contains tangible numbers. The problem here is this ds and this c. What does it look like to integrate over a curve c or to take a step ds? What exactly is ds? How do we express it in terms of x and y? Let's answer all those questions now. Our goal is going to be to express ds in terms of some differential that we have tangible bounds for. So our first step is going to be to convert this ds into x and y coordinates, because we know how to work with those. Let's look at a general case first, where we have some random undefined curve c and some given function f of x, y, working again in a 2D input space. ds, as we defined it previously, is an infinitesimal step along our integrating curve c. We can think of this infinitesimal step as a step in the direction tangent to the curve c at a given point. And now, this tangent step can be expressed in terms of infinitesimal steps in the x and y directions. dx is the x component of ds, and dy is the y component. From this drawing, we can now see that ds can be simply found using the Pythagorean theorem. ds squared equals dx squared plus dy squared, so ds is the square root of dx squared plus dy squared. Let's substitute this into our original equation. Okay, that's a step forward. We've gotten rid of ds and put it in terms of dx and dy. But now this doesn't look like a traditional integral. We've got two differentials in one integral, and the differentials are in a square root. It's a whole mess. On top of that, we still don't have proper bounds for our integral. Luckily, there's a way we can fix this. Parameterization of the curve c. What does that mean? Well, this curve here can be written as some function of x, y equals f of x. We know that any function written like this can be rewritten as two functions, where y and x are both a function of some new variable t, which we call a parameter. For example, if you have the function y equals 4x squared, you can rewrite that as y equals t squared and x equals t over 2, so that when you substitute x of t into y of t, you get the original function. Let's say that we can generally parameterize any curve, including our integrating curve c, from a single function y of x into two functions, y of t and x of t. X of t describes the x component of our curve, while y of t describes the y component, both conveniently written as a function of t. This also means we have bounds for our curve, going from t0, which would output the starting point of our curve, to t final, which outputs the final point on our curve. So, how does parameterization help us? Well, this is where things get a little hand-wavy, so stick with me here. Let's take our integral and throw in a dt over dt, not changing anything, just multiplying and dividing by a differential. Now, let's move the dt in the denominator inside the square root. When we distribute it out, what we see is that we're left with two derivatives inside the square root, dy dt and dx dt, which we can write also as y prime of t and x prime of t. Since we have functions y of t and x of t, we can compute these derivatives rather easily. And now we've practically solved our problem. All that's left to do is to rewrite our function f of xy in terms of t, add in the bounds we defined for our curve, and bam, we're done. We have a tangible differential, dt, that gives us scalar bounds to integrate over, and everything inside the integral is defined in terms of t. Awesome! But we can take this formula a step further. What if we want to take the line integral of a 4D function? In other words, one with a 3D input space. Well, all we need to do is adjust this ds term by adding in a third input variable, dz dt. And what if we're working in a 4D input space? Well, then we add a fourth input variable. Now, you can see how this equation would get quite long if you have a very high dimensional space, and also inconveniently it changes if we're dealing with different size input spaces. So now the question is, how can we generalize this? Well, let's step back to a previous video where I said the following. VVFs are equivalent to parametric representations of functions. And that's the answer. To generalize this, we can use vector-valued functions. As a reminder, vector-valued functions output a set of vectors that point from the origin to points on a curve. To construct them, you can just take the parameterization of a curve that you already have and throw on an I hat vector to the x of t term and a j hat vector to the y of t term. This entire vector-valued function, called r of t, describes our parameterized integrating curve in any number of dimensions that it may exist. So, how do we describe this clunky square root in terms of r of t? Well, with a bit of math, we can see that this is just the magnitude, or norm, of our derivative of our vector-valued function, or VVF. Remember that vector magnitudes can be calculated by simply applying a sort of Pythagorean theorem to the vector, squaring each component, adding them all up, and then taking the square root. Therefore, by taking the derivative of our VVF, and then taking the magnitude of that derivative, we end up with this square root term that was ds in our integral. Nice! So we can simply substitute this VVF derivative magnitude for our square root component, and then also substitute x of t and y of t for just r of t. And bam! We've got our line integral formula written in a tangible way that is generalizable to any number of dimensions, all thanks to vector-valued functions. Now, let's see what this all looks like in an example. Let's use the example I was talking about earlier. The line integral of the function f of x comma y equals x squared plus y squared over a straight line segment going from 1 comma 1 to 3 comma 3. We'll start by defining our integrating curve in terms of a parameter t. Luckily, our integrating curve is really simple here. It's just y equals x. So we can parameterize it as y equals t and x equals t. So our vector-valued function for this curve is just r of t equals t I hat plus t j hat. This means our bounds are pretty simple as well. Going from 1 comma 1 to 3 comma 3 would be going from t equals 1 to t equals 3. Now, let's find the vector norm of the derivative of our VVF. The derivative is just I hat plus j hat, since both terms have a derivative of 1, and so the norm of the derivative is just square root of 2. Now, let's look at our original function, x squared plus y squared, and write it in terms of t. Well, since both x and y are equal to t, that just makes our function 2t squared. Now, throwing on our bounds, we can see that we're left with a pretty simple integral, which we can evaluate analytically like so. And we find that the result is 52 root 2 over 3, the same value I presented earlier for this line integral. As a side note, the example I chose here happened to be a very simple one because the derivatives of our VVF were constants. You can imagine that for an integrating curve that's slightly more complicated, this line integral can get very nasty to evaluate analytically, and sometimes even impossible to evaluate at all. For example, if your integrating curve is something like x cubed, we can parameterize it pretty simply as x equals t and y equals t cubed. However, now the norm of our r prime of t term contains an x to the fourth term inside of a square root. And inside the integral, this square root term is multiplied by another term. This makes this integral very difficult to evaluate analytically, and sometimes impossible. Ultimately, that means choosing your parameterization efficiently can be very important, because some parameterizations will make the integration much easier than others. And that's pretty much all I've got to say about line integrals of ordinary functions. In the next video, we'll talk about taking line integrals over vector fields, and we'll see why that is so important to the study of multivariable calculus. Thanks for watching, and I'll see you in the next one.